Okay, so today will be a bit more intense. I have 1 hour and a half. It'll be mostly in the blackboard. And so, title of the lecture, my second lecture, will be Irreversibility. And entropy reduction. From, as I say, title here, from single stationary trajectories. Single stationary trajectories. Molecular models. Okay, this is a bit of a broad topic that I will discuss in more than one lecture, but you can. An advanced topic, molecular models. But the idea, let's say, one slide or one figure, or the idea of what I'm going to discuss today is the following. Imagine you have a motor, molecular machine, that moves in a filament. Okay? This motor carries a cargo in the cell and moves in one direction. Imagine that you do an experiment and you track the motion of this motor with an optical fusion experiment, for example. Then you will know that the motor takes fuel to move. Like any machine, if you want to move in one direction, you need to use fuel. So we use chemical reactions. Typically, you will use ATP. It's a molecule that is hydrolyzed into ADP plus P, and this gives energy to the motor to make a step forward. But something very important in experiments is that typically you are not able to see these chemical molecules that the motor is spending. You cannot see the fuel. Typically, what you can see is the motion of the motor along a filament. So, for example, we can call this X. You can see how the motor moves stepwise in an optical fusion experiment. So you will see something like this. But the motor, you can see that it's jumping between different monomers going up. Like this, random times. Okay? Which will be time. Okay, these times can be different. Okay? Very quick jumps also. And sometimes there are backward jumps. So the motor is so small that it's extremely influenced and perturbed by thermal fluctuations. So you will see the motor, even though it has a net current moving towards the right, sometimes it makes steps backwards. And in a typical experiment, you get this type of time series, which contains two things, dwells and jumps. Okay, so you see the motor roughly. You could discretize this trajectory and have it like this, like in steps of the same length. Length could be L, okay? And discretize the trajectory into a continuous time Markov process. Markov, okay, we will see later if it's Markov in general or not, in which there is hidden information, because you see the X, but you don't see another variable which could be, in this case, for example, how many ATP molecules is the motor spending in time.
Sorry, just to clarify, this X is only the walk along the...
The walk along the microtubule or along the track. Okay. This will be X, and it's a typical observable in an experiment. There is another hidden variable that is the ATP consumption. Function of time, you will have Y will be the number of ATP molecules hydrolyzed or synthesized. So if you do a step and you, for example here, if you do a step forward and you spend one ATP molecule, you will say that you start from zero, and at this step you consume one ATP molecule. This would be the full information in a, say, stochastic motor.
So there is a, I don't know.
Then, okay, 1 second. Then when the motor walks backwards, it can be many things. It could be that is a thermal fluctuation, and there's no ATP consumption. So it could be that in this backward step, this is the number of ATPs hydrolyzed is 0 here. So it could be that you stay like this. Okay, up to here, of course, there's nothing. And maybe in the backward step, like this one, there's nothing happened. Okay? But it could be there are motors that when they move backwards, they synthesize ATP. So there are motors in which in the backward step, this would be a jump downwards. And so typically, in this type of models, you have a random walk in 2 dimensions. One is the x, the position coordinate, and y is the chemical coordinate. In the most general molecular motor, you will have a random walk in 2 dimensions, okay? With some drifts. But, one second, the most challenging thing nowadays, one can have very precise experiments and even see the ATP molecule being expanded. But in most typical experiments, these dimensions you don't see. So you will be left, this will be hidden. Okay. Hidden. And this will be the only thing that you are left with. A track, okay, a trajectory in the x dimension in which you see the position of the motor. Okay. There was a question. No, wait, let's finish this question first.
I mean, ideally, like when a motor works on a microtunnel, also has like it can unwind stochastically.
Yes.
And also, like experimentally, is it possible to like generate very large trajectories of only walk along the motor,
Yes.
along the microtunnel?
Yes, but typically you also cannot resolve the binding and unbinding. So you only see the projection along x in most experiments. If you have resolution to see the motor jump, binding and binding, it's even better because you have one extra degree of freedom. But in most of the cases, you don't even see this. You just see the motion of the motor indirectly because you will have an optical tweezer trapped to of the particles moving in the tweezer. So that's the most typical situation. Binding and binding is more complex. So today I'm not going to be in that in such a big level of description, but I will just think of a motor where it spends chemical energy and I can only see a mechanical variable, which is the position. So this will be hidden.
So these are not the GFP experiments.
No, not GFP. No. This is a single molecule with optical tweezers. GFP experiments in principle.
And the experimental resolution of microscope, like the frame rate, that can capture all the typically like the
Yeah, you need a kilohertz sampling to see fluctuations. Of course, the steps, think about the steps of a motor, it takes around 1 second to make one step. So you will have 1,000 data points per step.
My point is there any chance of losing information? Like
In discretization, yes, of course. So the main message I want to give you with this first teaser for this is a bit of a teaser for this camp, is that in biophysics we can do models that contain infinity degrees of freedom and a high level of complexity, but in the real life, in experiments, we have partial information. We don't have access to all degrees of freedom, and not even we cannot resolve all the steps of a motor. So sometimes we will miss some of them. There was a question.
What is the length scale of the step in the first round?
The length scale of the step is around nanometers. So for example, a kinesin motor makes steps of 8 nanometers. Okay. So the order, so L is of the order of nanometers in molecular models. Okay. This is the length scale and the force scale, because you can put here an external force. The motor on its own moves along a filament, but you can put a cargo that exerts an opposing force. The opposing force that stops the motor, this is called stall force, is of the order typically of piconewtons. Okay, we are talking about very small step size and very small forces. Also, the motor is able to exert forces of piconewtons. So how big is this? This is an exercise that I ask to the students of my course in Trieste. So how big is FL here? So there is an energetic scale. So how much work you need to make a jump? That would be the force times the displacement, no? So if you multiply F, sorry, I put big F times L, will be of the order of 1 piconewton is 1 nanometer, no? Piconewton, that is nanometer. So the question now is, this appears in many biophysics books, it's a classical question. How big is the energy of a thermal fluctuation? It's KBT, you know this, no? So how much is KBT? KBT, you can try, we are in room temperature, 300 Kelvin. KB is 1.38 times 10 to the minus 23 joules per Kelvin, and multiply this by 300 Kelvin. Okay? 300 Kelvin. So you get around 4 times 10 to the minus 21 joules per joules. Okay? 10 to the minus 21. How big is this? Okay, 10 to the minus 21 is 10 to the minus 9 times 10 to the minus 12. This is 10 to the minus 9 meters, and this is 10 to the minus 12 newtons. So this is 10 to the minus 12 newtons, 10 to the minus 9 meters, which is 10 to the minus 21 newton meter, 10 to the minus 21 joules. Okay, 10 to the minus 21 joules. This is the energy, typical energy needed by a motor to do a step. And you see this is comparable to KBT. KBT is 4 piconewton nanometer. So if you want to remember what is the value of KBT at room temperature, the best is to use these units. You will always remember before. You will hardly remember this one. Okay? But this is 4 piconewton nanometer. So this means that a single thermal fluctuation can make the motor move backwards. This is comparable. So KBT is comparable to the energy needed by a motor to make a step. That's why fluctuations play a role here. You see sometimes the motor moving backwards.
So that means when it is detached from the tubule, then it may do diffusing.
Yeah, and diffusion in most cases will make the motor move backwards. There is a probability, non-zero probability. So you have e to the minus FL divided by KBT. This is not 10 to the minus 1000. It's 10 to the minus 1, maybe.
No, but even when it is not hydrolyzing ATP, on the attached on the microelement, it will do. So that is what it is.
Right.
Yeah.
It is not, but there is some detaching force, attaching force. What was that?
Yeah, but this will depend specifically on each model. Each model is. Today I will discuss very, very generic models, but you can ask Amitabha, he's an expert on molecular models, and each. So there is a community working on specific models. There's a big family of motors. Some of them rotate, some of them move along a filament, some of them big weights. Okay, each of them has a different energy, free energy of attaching, detaching. They are of the order of KBTs or tenths of KBTs. Something you have to think about also is how big is the free energy of ITP hydrolysis. Because on one side there are external forces that pull the motor backwards, but on the other is a chemical force pushes. So you should wonder how much is delta mu. So delta mu is the free energy change in this chemical reaction, mu ADP plus mu P minus mu ATP. If you think about it, say I have this in my lectures, and I have to check to be fully sure of the numbers, but I believe if I'm doing things well, yes, mu ATP is 14 kVt. This is of the order typically of 14 kVt. So you will have chemical push of the order 14 kVt. That's why the motor will move more in one direction. So it's driven by a force which is 14.
This is the maybe this puts the bias.
This puts the bias, exactly. And the bias has associated free energy change, which is 14 kVt. if the chemical reaction would be weaker, would be a free energy of 1 kBt,
Then it will.
well, then there will not be a very strong drift. So you need a chemical reaction that is energetic enough to produce steps. So you need to jump energy barriers of the kBt. Otherwise, it will be pure Bernoulli.
So should it be ATP minus ADP plus BP?
No, this is the chemical. The reaction, the chemical reaction is going from ATP to ADP plus B. So this is the free energy of the product minus the free energy of the reactant.
So what excess ATP is still there even after hydrolysis?
Exactly. Okay, so this is what I'm going to discuss. This is the setup. I'll talk about molecular motors, but and the question I would like to answer is the following. Imagine you are in an experiment and you record one of these trajectories. And the question will be, this is what I tried to explain or we investigated in this work, 2010, is what can we do with this single trajectory? Imagine you do a single experiment. What can you say about the entropy production or the dissipation of heat of the motion of the molecular motor? Think that here the molecular motor is spending ATP, so it's dissipating chemical. So some of the chemical energy that recedes is dissipated to a thermal bath. So the question we would like to know is whether we can use the information of this trajectory, and in particular the irreversibility, how irreversible is this trajectory, to estimate the entropy production in the motion of the motor. Okay? So here is, on one side we have the physics, and on the other side we have the statistical analysis of a time series produced by a physical model. So we would like to infer how much entropy production per unit time is produced in the motion of the motor from the analysis of partial information. Okay? This will be the goal of this lecture. Please.
So the fact that these are single motor trajectories is a statistical fact, right? Because you cannot control how many motors.
Yeah, okay, but you can do experiment with single motor, which is the simplest case. So, for example, you can do RNA polymerase and look at the motion of a single RNA polymerase in a DNA template.
I was thinking more kinescent sort of motors. There
There is a collection of motors.
There is a collection.
There's a collection of motors. The situation I'm thinking is a simplest one, single motor in a filament. And this is already complex, you see. This is already quite complex.
And just to read, so these were which motor that you analyzed in this paper?
Okay, I will introduce which. Here I will talk about single motor, not a collection, but one can generalize later on. Actually, a very good, the inspiration of this work was in a review, which I highly recommend you to read. This one, Modeling Molecular Motors. This is really, say, a masterpiece on this topic. Which summarizes most of the findings and the generic principles of the motion of molecular motors. This is 1998, okay? And just to say that I see most of you work in active matter, and you are very excited about this topic. So it's a recent field and there are lots of developments, but in biophysics, active matter is a key concept that is known for quite a long time. And already here, in 1998, there was a review, which means there was a large amount of research up to 1998, where already they knew and they understood very well most of the key concepts of what means activity and how can you make a molecular motor move in a given direction. This is really key. No? So,
and the movement of cargo in the molecule, that microtubule, is only due to that ADP conversion, or it may be due to some concentration gradient or like chemotaxis also. Some gradient may be there, not using that.
Okay,
Yeah.
This is what I'm going to explain now, and it's explained in this review, which is how a motor manages to move in a given direction, to transport, even though it doesn't have an engine inside. So, as Adam was explaining, molecular motors are not able to generate thermal gradients at small speeds. Here is explained why and what is the time scale that the small thermal inhomogeneity can last. And they calculate that this is around microseconds. So if you are able to generate a thermal gradient in a monomer, in the length of a monomer, this will last 1 microsecond. You can calculate, you can do the calculation, so it's really useless to use thermal gradient. So scientists were extremely motivated in understanding how can you manage to obtain net motion in an isothermal environment. Okay? And this, one of the key concepts, which is explained here, is the so-called flushing ratchet model. It's called ratchet as well, but it has nothing to do with the Feynman ratchet. It's a bit inspired because ratchets typically are used to, I need to disconnect, are used to describe rectification of thermal fluctuations. So it means getting profit from thermal fluctuations. The ratchet mechanism means I take a thermal fluctuation and I get profit from it. In the sense, I can move a wing out of the thermal fluctuation, right? So, please.
Small clarification. So, the KVT is of the order of the FL, I mean.
Yeah.
So,
Depends, okay? Depends, because here you can take an optical tweezer or a pipette and pull the motor. Pull the motor, so, okay. Wait, I have to reply. I'm happy to, I have to reply. You are bombarding me. Okay. No, questions are really welcome, and we are here to discuss questions, okay? So this is really the best. So there are experiments, for example, by, okay, these are the 1990s. It's not, you can measure the net velocity, so what is the slope of this curve, net velocity, as a function of the amplitude of an external opposing force. Okay? This is the, you can check the papers by Steve Block, or the lab, this is a very important lab in single molecule, or Carlos Bustamante. Bustamante, they are both in California. Wow, Bustamante. You can hear. Steve Block and Carlos Bustamante, they are the leading, some of the leading labs. There's also Felix Ritor in Spain. These are different labs where they do single molecule experiments, and they can measure mean velocity as a function of the external force, which can be an experimental parameter. And of course, the more you push, this is minus M, okay? This is the amplitude of the force. The more you push, the slower will go the motor. You can see something like, okay, something like this. Okay. So of course, for force 0, the motor is autonomously moving in a given direction, but you can push and push and push more, and at forces which are of the order of 10 piconewtons, you stall. The motor stalls. So on average, it does not move forward or backward. Still, it fluctuates, so it's moving right and left. Okay. Then if you pull more, of course, it will move backwards. This point is called stall force. It will play an important role in my lecture. Okay. At this point, the motor seems to be in equilibrium because it's moving equally right and left. But it's not in equilibrium because it's spending ATP. So in X, you will see no current, so you will do it like this. But in Y, there is a very high current, it's dissipated.
My question is regarding the correlation between the two, exactly. So,
Yeah, correlation. If you don't see Y, you have no idea. If you would be able to see, to infer with some techniques, I don't know, data analysis techniques, infer that there is something hidden correlating to this, it's beautiful and it's useful. Now your question.
So there is only one motor and try to see the experiment
Yes.
to one motor, single motor.
Yes.
But there is a collective motion of motors, and they are all interacting with each other in their movements.
Yeah.
So how can experiments generalize a single motor path to the collective motion of interacting motors?
How can one do this? There are different.
Theory develops.
We can do, I think I explained this in my course in Trieste. You can do different assays. So there's one assay in which the motors are, the head is attached to a substrate. Here are the legs of the motors. Okay, you can do this type of experiments and put, so the motors are close by, and you can put either a filament here, and look how the filament is. It's like the motors are doing like this and moving the filament. Or you can put a bead also. You can put a bead. And the motors are walking, and all of them walk in the same direction, and they start spinning the column. This way you can see effects of collective motion. This is one way, but there are also experimentalists that are able to do two filaments. Have to remember how it is. Forgot about it. There's one motor here, one motor here, and then they interact between each other. And they're able to see the motion of the two filaments. And in some situations, the filaments work parallel, in others work anti-parallel, etc.
But I think her question was that usually there are a collection of motors. How can you extract like the single motor? Is that?
But yeah, this is okay. This is a complicated question, but you do very low concentration, so you dilute a solution with many motors until. So first of all, this will depend highly on the molecular motor, and it will depend highly on your experimental setup. So if you are in a solution where the concentration of motors is very low, I have seen myself this experiment because I was collaborating with a lab for a long time. And typically what you have, for example, in RNA polymerase, is you have two optical tweezers that trap two particles. These are, give me a second. These are, one of them is coated by DNA, and then one, you touch the other and you make like a ladder, like this is DNA. And then you have to wait until you fish one RNA polymerase. And then the RNA polymerase are in solution, and at some point, one of them attaches here. And then, all of a sudden, magic, this filament starts stretching. So you start seeing this bit moving here. But in single module experiment, this takes quite a while until this happens. So it's not that you can pick a motor and put it here. You have a solution and you have to wait until this molecule binds here. And when it binds, okay, there is a probability that the second one comes. But you will see it in the trace, typically. Second one comes, there's a traffic jam, and you will see that it stops. It's difficult if you are blind to the molecule to see what's going on. You have to do inference, you have to have the criteria, statistical criteria. But typically, it's a much more challenging thing than what you think. It's not that you will put 1,000 motors and they will all work. It will be just a big luck that you take one in a single experimental day. So in most experimental days, they have the lab, they have the setup, everything is working, and they don't catch anything. Okay, this is the typical experimental day. 1 out of 20 days, or 30 or 100, depends on the lab. You will pick one, you will have one of these traces. Okay. So luckily, if you are a theorist, you can do a simulation every day, even though. Okay, but most of the simulation you trust them because they are not good quality, or okay, you made an error in one line of the code. But here it's a serious, very serious thing, very complicated.
Delta means 14 orders of the 14 into KBT and but this so delta means you always greater than this thermal fluctuation. So why it is like having this backward motion in this extreme?
Okay, because you are doing this type of experiment where you are pulling. Otherwise the motor will go and so on. Okay? So you need at least to have a confining or a force that keeps the motor, prevents the motor to get out of your experimental observation region. Okay?
By doing this, we are extracting like the properties of this water or something.
Yes. What we are doing in this way is you are studying how the motor moves as a function of the external force. This would be the ideal case where the force is 0. So you look at, okay, wild type motion of the motor. And in these other cases, you are exerting an external force, and you want to see how big is the load that the motor can carry, which is more close to the real life, to the real situation itself. Motors are not working on their own, free, so they are carrying cargoes. They are either attached to filaments, they carry cargos, they are designed to exert power. So this is important to understand. Okay. They move vesicles. The vesicles that are transporting the cell, they are not moving only by diffusion. Otherwise, we will be all dead. You need a quick transport system. You need, and the cell is made of filaments, which are like highways. Where I think you can compare this more to the traffic in Mumbai. So it's really crowded, and there are so many, and they move on. They have a direction, but there are fluctuations because there are many. And so this is important. Otherwise, if you only rely on diffusion is very problematic, because if you want to reach, you calculate the first passage time from here, from point A to point B, by pure diffusion. This scales quadratically with the distance. This is not interesting. You would like to, okay, if I go somewhere which is double distance, I take 4 times than what I want, it's not good. So I would like to, at least it's linear. So if the first passage is linear with the distance, it's better.
Like inside a body, like there are many like different environment. So, but how can you like do it in an experiment? There can be like some active noise as well.
No active particle. This is much simpler than that. The activity is inbuilt. There's no genus particle. This works on its own. So active matter is already in cells. You don't need to exert active noise, nothing. This is in a bath, this is in water, and there's chemistry, and this works. So it's not man-made active matter. This is within ourselves.
I wanted to ask you.
Because this is a slight vibration. Because
I think I will be able to explain 1/10 of my lecture today. No, but I mean, it's not a big problem, because then the last lecture they planned it will be the half of one of these. So I will have to reschedule my course. I will not be able to explain everything I wanted. It's not possible. But questions are important.
Yeah.
But maybe we have to bound in each slide, please ask only one question. For each of you. No, we can ask you later. Sure.
Just one, like, this is probably a chemistry question, but the plot of velocity versus force in flow initially has a plateau, right? A naive expectation would have been direct a straight line, right? Something like a Boyon's force and terminal.
Yeah, typically it's like that. I was a bit discreet here, but most of the times it's like this, exponential. You can do simple models when it shows exponential, but it's not always exponential. Sometimes it's linear, depends on the model. Okay, good. Let me try to continue, because I just wanted to explain first, very briefly, the flashing ratchet mechanism. So, flashing ratchet mechanism is the following. So, think about, as Amitabh was explaining before, of the following model in which you have a polar filament. The motor is moving. And the motor has 2 configurations. Either it is attached to a filament, it's attached, and when it is attached, the motor experiences a potential that is space dependent, that we will call P1 effects. And we will say that the motor attaches and detaches from the filament at random times. So there will be an attachment and detachment rate. Okay, again, you have the same situation. Here will be detached. Okay, to be detached, it could be a configurational change. So what I'm going to show later on the right will be a very generic description. So here will be detached, or this could be configuration A, configuration B. Detached, which means that it's experiencing a second potential P2X. And the motor is just attaching and detaching in a polar filament. So the filament is polar, which will mean that the potential that the motor experiences are going to be slightly asymmetric in space. So this can be described with I'm trying to find the case. This can be described with a very simple continuous model, which I will later simplify. And this model is called the Flushing ratchet. And in the review that I just explained, that I told you, it's described as follows. So you have in the y-axis Px, which will be the free energy of the motor. The free energy of the motor. And in x, we will plot the center of mass position. The x, which is the center of mass position of the motor. And what I would say is the following, that there are two potentials, and the motor, the center of mass of the motor is represented as the position of a particle. Okay, of course this is a bit of a simplification, and the potentials are periodic. Okay, it's periodic because we have a periodic structure in the filament. And moreover, these two potentials are periodic, and say one has a different energy than the other, so it could be something like this. Yeah, periodic, and both have period, the same period n. Okay, this is n. So the motor is either in the lower potential, which I will call P1x, or in the upper potential, which I will call P2x. And the current position of the motor will be, for example, the motor is, let's say, here. Okay. And as I said, we will assume that there is a switching or flushing between the potentials. So if the motor is here, it is experiencing diffusion, so it's experiencing thermal fluctuations following a Langevin equation here. And then all of a sudden, this potential can be switched to the other potential at a random time. The motor falls here. It's not falling anywhere, so the position is not changing. It's only the potential that experiences. And this happens at a rate that I will call omega 2x. Omega 2x. So this rate, I will assume that in the most general case, the switching rate will depend on the position of the motor. That's the most general case. Okay? This is omega 2 of evaluated at x. And vice versa. From here it can be switched back with a rate omega 1x. Okay? So you can think of many possible switching rates, even constant. You could say there is a constant homogeneous rate of switching up to now. Okay? So this is the so-called Flushing ratchet. It is
x dependent or it's a periodic, right? Like
the potentials are both periodic and the rates are both periodic. Okay. So V I of x, I is 1 or 2, is V I x plus minus n. For all x in R, it is periodic. And also the rates. Omega I x is omega I x plus minus n, also for x in R. Periodic. Periodic, but, very important, they are asymmetric. Symmetric in the sense that if you flip the x-axis, they flip. Okay.
Just related to this earlier thing you were saying, in principle these omegas could be functions of your hidden variable also, the y.
Of course. It will appear. This will appear later. Okay? So, this is the general setup that I'm going to explain.
So, and then V1 is symmetric, the second potential is symmetric, or both?
In general, I consider both asymmetric. In general. But you could have, for example, V1, this will appear in the model I will use later, V1 equal to 0, flat. And 0 would be its free diffusion. This is one specific example of this theory is V1 flat. Okay? You could have V1 equal to 0. You could have V1 x equal to 0. This means free diffusion in V1. This is one example. It would correspond to the case, well, it will be, this case will be free and the other will be attached, but it doesn't matter one or two. Okay?
Excuse me.
Yes.
These omegas are the transition rates that you wrote?
Yeah, these are the switching rates.
Okay.
Because be careful of one thing. There are some transition rates within the potential. So the typical motion will be the particle is here, is diffusing, 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 it's trying to climb the potential, so on. So there are transition rates within the potential. And then at some point, boom, it will fall down. And then it will be falling, 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 and then it will switch up. Switch down, switch up, okay? The key point is that for most choices of these two functions, for most of them, you will have a current. So by switching two potentials, you will have net motion. This is called the Lecture-2 effect.
So although transition rates are same, the probability of you being in, say, the V2 state is much larger than, or the V1 state is much larger than.
It will appear now. I will just explain this. So the key point here is how to choose these two. Okay? How to choose omega 1x and omega 2x such that you have motion. So the question would be, are there choices of omega 1 and omega 2 that generate a net motion? This is the question I would like to answer. And as you may notice, it depends. So imagine I have Dieter balance. Let me assume Dieter balance. Now what is Dieter balance? Dieter balance means the following, that the transition rates are related by the energy difference. So when Dieter balance means equilibrium. So I have two energy levels, and the transition rate from the low to the high divided by the transition rate from the high to the low energy will be e to the minus beta times the difference of the energy. That would be usually called Dieter balance. So Dieter balance means that omega 1x divided by omega 2x equals E minus beta. There's no effective temperature here, right? There's no complicated things. Beta 2 minus E1. So see that omega 1 is the transition rate from 1 to 2. So it should be written. Okay? Beta, remember, is we are in an isothermal environment. So beta is 1 over kBT. If you assume Dieter balance, one second. If you assume Dieter balance, what you can show is that the motion in this periodic passive potential switches is equivalent to the motion in a single periodic potential. This is the effective potential. The next single potential that is periodic. So df x plus minus f equals bf of x. This is what you can show. So do this. It's okay. It's a bit long. So this is written in the review, but you can. Okay, I will do a small box how you arrive to this, and please have to trust me a little bit. So what you have to do here is first consider this process. You have two potentials, so you can write a Fokker-Planck equation. Remember, in continuous systems, what Abhishek Dar was showing, there's a Fokker-Planck equation. Okay, so you will write something like this. Typically, you will write partial T of P1. This will be the probability that I am in state X and in potential 1. Typically, you will write like this, no? Minus partial X of J1, the current if you are in state 1. Typically like this. But it's not enough, because now we have switches. So it's not just a Fokker-Planck equation, it's a Fokker-Planck equation with sources. So there is something else here. So the something else is the following. Actually, I can move this to the left, put with a plus. And this something else is the switches. And the switches, I remember this is B2, this is B1, this is omega 1, omega 2. So for P1, you have a loss term with rate omega 1. You have minus omega 1, P1. I am forgetting about the X, but this is notation. Plus omega 2, P2. And the same for P2. That's an X, J2, omega 1, P1. Now the signs have changed. And okay, this is the equation, the Fokker-Planck equation for this model. Okay.
Is the P effective cause due to the optical reason?
Sorry.
Is the P effective cause due to the external?
Okay, this is the model, the original model for which this is the Fokker-Planck equation. Okay, and then you can show that this can be written later on as a Fokker-Planck equation for one variable in a periodic potential. No optical reason. This is just math. This is just doing this model. Okay. So again, I'm going to write the currents briefly. So the currents are Fokker-Planck currents. So there is mu1. Okay, I don't know if this is necessary, but minus partial x p1. Okay. P1 and minus d partial x p1, and the same j2, the mobility minus partial x p2. This is just doing function d partial x p2. Okay, and
So here everything is 1, 2 like those states. Because P1 is the probability of having.
Let's see. So P of x, this is the probability that the motor is in x and in any state, 1 or 2. This is written as P1x plus P2x. So I'm breaking, okay. In reality, we have a joint. We have two variables, x and a variable sigma, which is the state. Here I'm summing both. Okay. Each of them obeys Fokker-Planck, but they are connected because there are rates that connect both. And this is the total probability, will be the sum. So you can show that from these equations, you can show that if you have, very important, this condition, I'm skipping the mathematical details, but you can try yourself at home, you get a one-dimensional effective motion here that looks like this, partial t of p equals.
So this P of x is normalized, of course, but P1 and P2 individually may not be normalized.
They are not normalized. They are not normalized. Okay? These are not normalized. This one is normalized. Yes. Okay.
Sorry,
Yes.
the D shouldn't be different when attached, when it has the D.
It could be different, yes. We could go like this, D1 and D2. Yes. It could be different. That's why I put here mu1 and mu2. It could be different. The more general theory is they are different. This is what this is the different.
This is the 3x, this kind of which we are taking as a solution. It can be multiplication of the superlative.
Sorry?
The px can
Why is like this? This is very simple because in reality, you can see this as a Fokker-Planck equation for a system which has two variables. One is x and the other, we can call it, so there is x, which is in R, and there is a sigma, which, well, sigma is not a good letter, but sigma, which can be 1 or 2. This is the state of the potential. Okay? But there are two variables. Yeah, I'm trying to trick you a little bit that there is one variable, only x. No, there's a second variable, y. Y is either 1 or 2. So the full description, microstate of the system is x sigma. So in principle, you have to formulate everything in terms of p x sigma. If you know x and you know sigma, you know everything. Where is your motor? Okay? X tells you what is here. Okay, let me be here, for example. But it could be potential 1 or 2. So to fully specify the state, I need a second variable, which is the state. Yeah. This is the probability of the motor to be in x and to be in potential sigma. And this is the one that must be normalized. This one has to be normalized in x, minus infinity to plus infinity, and must be normalized in sigma. Well, sigma, you have to do a sum over sigma. This should be equal to 1. Okay?
And I am unable to follow that why there is two potentials, V1 and V2.
This is the model. The model is defined as two potentials. And what I'm going to show you,
What motivation?
I told you before,
Okay, that
the model has two configurations.
Okay.
One could be attached, in which it experiences a potential, okay? It's moving it can move even if attached.
Okay. Even if detached,
It can move. And the second is detached, in which it still feels a potential, but it's different. And it can move while detached. Of course, attached detached is the most crude simplification. It could be that the motor has two configurations. The motor is like this, or the motor is like this. Okay, it has two configurations. And then, even depending on the configuration, it will also experience a different form. Also, it could be the two legs. It can be so many things. But this is like the minimal model to generate motion. Two configurations. We could do with three, but then do the math. Okay? I tell you, this is not trivial. You start from here and you show that then the total probability, or the marginalized probability for x obeys minus partial x j, in which there is this j has an effective potential. So now this j would be j equals mu effective minus partial x d effective times p minus d effective partial x p. So try to manipulate this at home. It will take you a while. And extract the effective potential, and you will show that the effective potential for this choice, for detail balance, the effective potential is periodic. As I show here, it is a periodic potential. And now I ask all of you, what happens if you have a particle in a periodic potential? What do you expect? It will fluctuate, but what will happen?
Stay there.
It will stay there. There will not be current, a net current. It will not move on average. So this will have mean velocity, which is the mean current, will be zero. So this has zero current, or mean velocity equal to zero. So the motor does not move. So if we satisfy in this rate detail balance, the motor doesn't move. Okay. This is something you can check. Even in simpler models, discrete Markov, etc.
So it's only periodic or symmetric about?
It would be asymmetric in general, asymmetric, but periodic. But in general, asymmetric things. I'll give a simple example and check. Typically asymmetric. A very simple case is when you have flat and asymmetric. The effective potential will be asymmetric. But periodic. So then
Density is enough for saying average V is 0.
Not energy is zero.
No, average V.
Okay, velocity. Okay, we could say average current. Okay.
So you're saying the effectively also is an equilibrium dynamics.
Sorry?
Effectively also is an equilibrium.
Yeah. Yeah, because it's wrong. Yeah. It's like a dynamics. So now let me go to the most interesting case, which is, okay, you should see that to do this in an experiment, if you want to do an experiment where satisfying detail balance, it's okay. It's not so simple. So it's, some people call it the miracle of equilibrium. No? Equilibrium manages to have this relation. But if you choose any two functions, omega 1, omega 2, typically it will not be satisfying detail balance.
So it can just here you have this stalling thing, right? Here detail balance is broken, but you don't have current.
Here I'm saying without exerting any force, so I'm at zero force. At zero force, I have zero velocity. Okay? What I'm saying is molecular motors at zero force at positive velocity. This is the. How come we can get this? Okay? This is the question. This is the question. This is the question.
Sir, why is the switching of rates not a non-equilibrium process? Like switching from V1 to V2, one can also think of it as a like non-equilibrium process.
Let me explain what. You can repeat the question in 20 minutes. Please.
I mean, if you are having a asymmetric potential,
Yes. Yes.
so can you quickly motivate like only periodicity, how periodicity says average is, I mean, because if I consider a particle set at the bottom, it is asymmetric, so more probability is going, one side is more or less,
Yes.
right? It will affect.
Yes.
And then, I mean, it will hop to next position.
It will hop, but it can also hop backwards.
So that's what, so that will create a net current, right?
No.
Average is zero.
Average is
Average is zero.
average is
Backward.
That is the detail balance thing.
Okay, I'll go. Wait. I go to your two questions after I explain this. Okay. Otherwise, I'm not able to explain the main sense of it. So let me think of broken interbalance. What happens if you break the interbalance? So one possibility to do this, as I explained in the review, is that you include a second channel of transitions by ATP. You can do this in different ways, but one way that is very elegant is to do as follows. Omega 1x to be two parts. One is this one, omega x, and the second one we will call it alpha x e to the beta mu ATP, and times. Okay, this is one choice, but you can have many. d1x, and the second one will be omega 2 of x will be omega x plus alpha x. There are infinite choices you can do, okay? Infinite. E to the beta, to break detail balance. So the key point is that to have detail balance, there's only one choice. It's that equation. And to break detail balance, there are infinite choices. It's whatever ratio of omega 1 over omega 2 that is different to e to the RHS. Beta mu ADP plus mu p is a chemical potential, so ADP p e to the beta v2 of x. So here I am distinguishing between one channel of the transition, which is thermal excitations, and the second channel, which comes from chemical reactions. Okay, so there's a sort of two contributions to each of the transitions here. You can either go up through a thermal excitation or through a chemical reaction, and vice versa. Okay? Both together will make a total rate omega 1 and omega 2. Okay, so if you do this, and trust me, this is really simple, you will see first that omega 1x over omega 2x is not obeying detail balance. It's not minus beta b2x minus b1x. You see it immediately. I'm taking the ratio, there is this quantity. So it's not going to be this. And one interesting observable that you can build out of this is the following quantity, is this omega of x. I'm really following the notation of this review. Is omega 1x minus omega 2x e to the minus beta v2x minus b1x. So omega is, if you plug in the rates from detail balance, omega will be zero. There is a quantity that measures how far we are from detail balance. You put omega 1, it's omega 2 e to the minus beta, this will be equal to 0. Otherwise, this will be non-zero. If you put these functions here, this will be non-zero. Okay? So this will be 0 if detail balance, and different to 0 if we have broken detail balance. Right? So, in particular, for this model that I show here, omega x, for this model is equal, you can do the calculation in one line, alpha x e to the beta d1x plus mu ATP times, and here comes the interesting part, 1 minus e minus beta delta mu. Okay? Delta mu, repeat, is this quantity, the difference. So it's the Gibbs free energy in a hydrolysis. And you see immediately from this simple model that omega x will be 0 when delta mu is 0. When you have a chemical reaction that has no free energy, there's an equilibrium reaction. As long as you have a non-equilibrium condition for the chemistry, you will have broken intervals in the simple model like this. You see? You see it from here. Moreover, if you say you can do the expansion, you will see that the larger is delta mu, the more you will break the interbalance. This is also important. So once you have this type of setup, you can try to repeat the same calculation that I did here. You can try to write an effective equation for the coordinate x, and you will have again the same form like here. Now it will be more challenging because we will not assume that quantity. So you will have to do the calculation for generic omega 1 and omega 2. But you can show after a couple of pages of calculation that the effective motion, like the one I explained here, is the effective motion. Now it will result in a diffusion in a potential that is now, however, tilted. So now the effective potential that is obtained when you break the balance in any way, the effective potential is not periodic. You have a tilted potential. Tilted effective potential. Okay? And now I ask you the same question I asked you before. What happens if you put a particle in a tilted periodic potential? What do you expect? In the long time, it will fall. It will fall. So there will be a current. There is a net current. The mean velocity of the mean current is not zero. Okay? When you induce the current, there is a net very. Okay? So by switching potentials at rates that do not obey detail balance, so you just need this condition. And doing this in an isothermal environment, you can generate motion, net motion. Okay,
So can because with this tilted potential, can one do equilibrium statistical mechanics and get that equivalent to?
Well, equilibrium. There is a current there.
There is not equilibrium. I am saying the standard method to the power minus that this one partition function, etc. Can one calculate?
Here you are in non-equilibrium steady state. Whatever you can apply to a non-equilibrium steady state, you can apply to this model in the effective description. Because at the end, okay, this is periodic, so you can think of, now you will study from 0 to 12 and say there are periodic boundary conditions. So whatever you learn in stochastic thermodynamics for rings, this is like a ring, or it's a roller coaster, no? A ring. It's a model that appears in all of the talk and his reviews. So it's something like this, no? So there is a ring and there is a torque. An external torque. This is a paradigmatic model of stochastic thermodynamics. It's a periodic potential with a torque. Please. Please.
I think continuing on this question, if you are at stall, then the potential will become flat, right?
Yes.
Then you can use all techniques of equilibrium.
Then yes. So this, as I said, is without external force. So my model, it's not my model, the classic Roldan model, induces the net motion, and then you should understand in which direction it goes the motion. And this, okay, this I will explain in a moment, but it will induce a net motion in this direction. Okay, so there is a current in this direction. But this is induced at zero force. So the motor is able, by changing configuration at random times, is able to move in a given direction. I'm saying here, well, I have solved this part of the problem. At zero force, zero external force, the motor is moving. Then, as you very correctly say, if you add an external force, the velocity will change. So you could do this, all the same development here, but adding a small external force here. You could do that. How things will change? In a very simple way. The only thing that you will change is that in the Fokker-Planck equations, instead of having only a conservative force, there will be also non-conservative. So you will change this thing, you will change it by minus partial x v plus f external along x. Actually, the f external will appear also in this part. It will appear. Yeah, you can investigate, and then it's interesting because then the stronger and stronger is the force, the tilt of the potential will be changing. So when there's a very negative external force, the potential will look like this. So will change it.
How are you exactly constructing this potential? How are you doing?
How is what I said like
So
you start from here and try to write. Okay, then you write the marginalized density. So it's the sum of T1 plus T2, and try to write from these two equations an equation for T. It's a lengthy calculation, but it can be done in a human time. Okay? So just sit down and try. So you can also take the results of the review, which is what I did. Take the results of the review and check they are right. So you pick this, in the review they give you the expression of the safety potential. It's a complicated function. It's a non-integral function. It's written in terms of an integral. Then there's the effective mobility, and there's the effective diffusion. So what I'm saying is that integrate these two, or sum these two things, work it out, couple of pages of calculations. For me it was 5 or 6, I don't know, and then you will see. Okay. I'm skipping the. I mean, if not, we only talk about math.
How important is the role of this alpha x? Alpha x is not periodic.
You can put alpha x periodic.
Because then in terms of the effective potential as a function of x, it looks like W on x is also periodic. W x is also periodic.
Omega x and alpha x you can put as you want. You can put them periodic, you can put them even constant. And still you
but the effective potential will be not
Still.
because of the delta. Oh, because the weightage will be the delta.
No, because of the breaks it around.
Yeah.
First here.
Is it possible to approximate the tilted potential as a linear plus periodic?
Depends on how large you put the potential. Depends on how big are the barriers. You could think of a simplification of a model instead of being smooth. They are like this, okay? And there you can do it. Sorry, there were 2 questions there. Has this solved your questions?
My question was like for this effective potential and diffusion coefficient, if I write this Roldan equation, will the noise in that be correlated?
No, not correct.
So
this is a standard Fokker-Planck equation for a Langevin equation in 1 dimension with white noise.
So, but the information about omega 1 and omega 2,
the information of omega 1 and omega 2 is inside the potential. Can show you in a moment. Okay? So if you are very curious, you can just go to the review and check. We got publicity this also. So you can go to the review, and at some point this is explained here. So this is the formula for the effective potential is here. And you see, if I remember well, there are this mu1, mu2, which is the friction in each of the potentials. W1, W2 are the potential. You have to do this integral. It's typically non-trivial. And there is this lambda. Sorry, the lambda is the ratio between lambda x is the ratio between p1x and px. And this will depend on omega, on the shape of omega. It's a bit involved. It's a bit involved. I'm really simplifying things. Your question was solved?
So my question was so my question was, we are going from V1 to V2 or V2 from V1. Is it not like a non-equilibrium process because there is a switching?
Yeah, of course. So this is what there will be non-equilibrium because I said, as I promised, I will relate the trajectory to the dissipation. There will be non-equilibrium. And actually, it's an essentially non-equilibrium process because you have a particle in an energy and you are increasing the energy all of a sudden. You are doing work. So typically, it's a non-equilibrium process. But if you have little balance, there will be the same number of events of going up than going down. They will compensate. So it will be equilibrium, miraculously. Okay? In the most general case, switchings are non-equilibrium. In the most general. But if there is this equation, it turns out the switches are equilibrium. Okay? And this you can get in a very simple model like two-state model. Two-state model, you are in zero energy and then you are in energy E. You are switching. But you can do the switches in a way you are in equilibrium. If the switches are in balance.
Okay, so then so then in the end, everything will be effectively like equilibrium.
Everything? No. No. This is exactly what I tried to explain. If the rates obey this equation.
Yeah, if given the rates obey relatively.
If little balance, yes, it's equilibrium. It is equilibrium because the same input energy that you put in switching up, you will give backward. You will receive it. So you have a machine that is switching the energy, inputting energy, and then outputting energy, following these rates. The net energy will be zero. But if you do it broken little balance, it will not. Okay? First meeting was.
So two things. So one is that if you, in the presence of external force, do these W1 and W2, the transition weights, are they also force dependent? Or?
You can make it force dependent. This will be even more advanced. Yeah.
And in that case, or even in this other case where you just have it in the current, does the stall force depend on the concentration of ATP? Like
in general, yes.
Is it true for actual motors? Because I just generally see a number. So
yes.
Is an ATP dependent or not?
You can do this experiment at different ATP concentrations, and you will have different curves depending on the ATP concentration.
So the intercept is different.
Intercept changes with ATP concentration because you are changing the delta mu.
Yes.
So typically the stall force, in order of magnitude, the stall force, here there is mechanics and chemistry, so there is a tug of war, one versus the other. So typically the stall force is of the order of delta mu. Delta mu is an energy difference divided by L, where L is the filament length. Okay. So FL has units of energy, delta mu has units of energy as well. So typically, the more energetic is your chemical reaction, you will need a higher stall force. So typically it goes like this. So the stall force will change with the concentration of ATP.
So the general numbers are like at saturating ATP, is that the understanding? Like whenever somebody says kinesin is 5 piconewton or something.
Yeah, so it means, what do you mean by saturating?
Like it's overflowing, it's full of ATP. So
full of ATP. There is excess
it's not
of
a
ATP.
limiting.
Typically there's excess of ATP. And there's so much that you burn some ATP, but roughly the ratio between ATP and ATP concentration keeps constant. Roughly.
And the other thing I just wanted to ask is that if you are like, the force is being applied, let us say, by an optical trap, so then it's not really a constant force ensemble. Depends on how much the model is worked. Does that make the theory much more complicated, or it can be worked out just as
It can be worked out. It can be worked out. Because nowadays you can do line level models, 1, 2 dimensions, other external force. It can be done. Yeah. I've seen papers where they have a flashing ratchet, and then on top of that there is a spring collet. And the collet is not in this flashing ratchet, it's in another potential. So yes.
I'll take the reference.
Yeah, there's a lot of literature on this. Oh, good.
Just one question.
Yes.
This force I thought it has to do with one reaction, right? How does it matter whether you have high concentration or not?
No.
It's just one exchange.
Be careful, this is the average velocity. So the average over a long trajectory or over many realizations. But of course you can have the motor in a path that has lots of ATP, so much that there are so many bindings, so it makes the motor move faster. So the force you will need to stop it will depend on the ATP concentration. Okay, typically. Okay, so here I'm drawing curves for different ATP concentrations.
Edgar, if I may ask now.
One second, because I will take a short note because this is a good idea.
So in this omega 1 and omega 2, can I think them of as the frequency at which either V2 or V1 appear in the picture? Is that the same? I mean, you talk about transition rates. That's what you mean, right?
Yeah.
So if your V2 is infinite, for example, then you always in V1.
Yeah, you could do that.
Something like
yeah, there is a limit. The limit of having one potential would be that. Well, you could put this one to 0 and this one to 0. Then it's free diffusion. Nothing will
So
happen.
if I put V2 to infinity, for example, then you just don't see V2 at all.
Yeah, sure.
But if you have some non-equilibrium process, say ATP or something, that can produce V2 out of somewhere.
Sure.
And then you start it.
These are from the very beginning. They are taking potential from the very beginning. Yes. So I don't know how much time we have, but just okay. So I think you understood that as long as I switch breaking little balance, I will have a current, and in particular, one of the interesting models that this is what I think I will discuss in the next lecture. Because I want to start with what I'm going to say now, but okay, it's fun. But then I don't talk about bullfrog, so it's okay. I think motors are already one of the most important applications of stochastic thermodynamics until now. Seeing a molecule. So one of the things is in which direction the motor moves, either to the right or towards the left. And this can be understood in a very intuitive way. So you can have, okay, an example could be, as I said, you can pick your favorite example. But let me take an example which is very simple, in which one of the potentials is flat. What I'm going to say is also valid to the most general picture. But let's say V2 is equal to 0. Actually, I will use this in the rest of the lecture. Let's say V2 is flat, free diffusion, and V1 has a shape that is like this. Okay, this is V1. And think about the following. I said, let's break little balance. So, in your opinion, what is the easiest way to break little balance? Which rates would you choose?
Should that be V2 and the bottom one be V1?
You could do that.
I mean, according to that equation.
But I don't want to have little balance because I want to move.
No.
But
Say
that's
very
notation. Notation.
Notation, I'm talking about.
Earlier you have used this V2 as the top.
Okay.
Just to.
That's a question.
No, I was asking like this, you draw this V2 even at a shifted place, like they can cross each other. I mean, this is a general.
Yeah, they could cross each other, yeah. They could cross each other. This is very general. They could cross each other, totally. Let me take a simple example. Flat, so free diffusion here, so if the particle is here, it's doing free diffusion, and if it's here, it's experiencing this sawtooth tension. So, give me an idea. How can I choose these rates in a simple way to generate a current?
The upper rate should be higher.
Okay.
So
This is
that
one
you
of
can keep on going to the right for longer time.
Okay, this is one very good possibility. Other? You asked me a lot of questions, but now I ask you a question.
What is the question? Sorry, what is
How? Give me a simple choice that will generate a current. A simple choice for omega 1 and omega 2.
Set one of the omegas to be 1.
1, 1, and the other?
And the other one in such a way that it will always be greater than 1.
Okay, that's a good choice as well.
So as long as you have some omega 2, there should be a drift.
Okay. What is it?
Upper one is exponential and lower one is power.
Okay. So, well, everything was magically true, but if you do this, up rate 1 and down rate 1, you will generate a current. That's it. Why? Because you're breaking the thermodynamics. So if you come here, you have B2x is 0, B1x is 0, so you put here at 0. B2x is whatever you want. But into the this is not equal to 1. So here you will have 1 divided by 1. It's not going to be 2. You will have this. So this will break the thermodynamics already. So in general, if you have already this case, a rate R to switch up and a rate R to switch down, this will generate a current. As simple as this. Okay, now people will talk about resetting, this thing, so it's similar to this Stochastic resetting.
But that is not in our hand, right? I mean, switching will be controlled by something.
It's not in our hand, this is in the hands of nature. So, well, in essence, no, what I'm saying is if you do an experiment with two potentials and a particle that experiences one potential or another, and the experimentalist has a computer, and the computer is switching these two potentials, it's a very simple way to generate a current, is to switch the potentials both at random times with the same rate. As simple as this. You see, because if you have here, okay, omega 1 was going up to, is omega 1x equals to r, and omega 2x equals to r. So you have omega 1x divided by omega 2x is r divided by r, which is 1. And this is different to e to the minus beta b 2x minus b1x. Because in this case b1x is 0, so this is e to the minus beta b2x. And see, b2 is always positive. So this is not equal to 1. It's not equal to 1. Exponential of something positive or minus something positive is smaller than 1. So you break it around.
So, I mean, if I make V1x as a time dependent, then?
Well, you want to complicate things more and more.
Yeah, I mean, that will be very easy because if I have something electric field signal,
sure.
time.
But here the thing is that can do spontaneously. You don't need to have external field. It's active anyway.
It's active anyway. So then the question is, okay, there will be a current. This is what you promised. But what is the direction of the current? Here or here? In this. You will move right or left?
Right.
Right is here. It's your right, yes. Okay. Yeah. So, and this can be understood in a very simple way, actually, because imagine you have a particle that falls here now, and then it will face a wall. So, it will be very difficult to jump the barrier, especially if this is much higher than KBT. So typically, if you wait, let's say these rates are small, typically you will reach a state which is peaked. This is the minimum of the potential, so at some point you will have a distribution that transiently would look like this. Okay? So it's more likely that it's here, because this barrier is high, no? So you will have a distribution that will look distribution that may look something like this. Okay? And some few particles, let's say you do many of these motors, and these motors are all independent. They don't see each other. By the way, in this review I showed you, there are also models where they are collective motors, so you can put, someone asked me about collective, so you could put many of these guys, switching all of them, and all of them connected to a muscle fiber. So in this review they talk also about collective things. But let me just stay with the one motor case. Imagine okay, you have either one motor and you do millions of simulations, or you have 1 million motors that are independent. Then imagine you start here, initial state, the rates are slow, so then they are starting falling, and you will have a distribution at time t that will look like this. Why like this? Because the motors are here, so they are facing this wall, so there are very few that are able to make this jump. But what happens next? Okay, there are these guys that made it. These are the very fit guys that are able to jump very high values, no? There are very few, but they're enough. They are enough to, then they are here. And few of these will be very happy to continue rolling down the potential. So these very few will make it and jump and continue. Okay? Then there will be switches. And you can do a simple simulation. There are even applets and videos online of this passing ratchet motion. You will see that this is basically an effect. It's a statistical effect in which at the end, okay, some of these guys will come here, there will be a small like this. This will, in the next run, or in the next switch, this will also, some of them will jump and so on. This will generate a net motion towards the right position. Okay? So it's induced by fluctuations.
So far, the asymmetry of the potential didn't feature anywhere in the equation.
Yeah, the symmetry of the
But
potential.
it seems it's very important here.
It's very important.
So where does it show up in the equation?
Yeah, it shows up here. It shows up here, because at the end, the potential needs to be asymmetric. So the effective potential, okay, you have this description, but then, sorry, the asymmetry that is induced, actually this is very subtle, very subtle.
That's the asymmetry of the effective potential. But here the effective potential will be, and most part will be played by V2.
Okay, there are two things. One thing is tilt, and the other thing is asymmetry. But as far as I know, to generate a tilt, you don't need asymmetry necessarily. I think we have to think.
No, I
How do you
think
choose?
this has to be asymmetry.
Otherwise, how do you choose the direction?
No, it's true. It's true. It's true. You need two things. Okay, you need two things. To break the balance, there are two ingredients. One, break the balance. And second is that at least one of the potentials, Z1x or Z2x, are asymmetric. In the sense, inversion symmetry, yes. The I, this one of x is different to the I L minus L half minus x. Okay. We need these two ingredients.
They didn't feature anywhere in those equations.
Why don't fit anywhere?
No, like, was it, did you use this fact?
Yeah, this is used in the effective description. This is used, where is it? This appears here. Okay, I have simplified a lot. So, you have this model. Then you write effective Pokemon equation with effective potential. The effective potential has a very complicated expression. I showed you before in the it is, this potential is tilted when first you break the balance, and second, when one of them is asymmetric. At this one of them, you need these two conditions. I was simplifying, but you need both.
You need both of them.
You need both. Okay. But this is typically, so it's more common that a potential, effective potential, is asymmetric than it is symmetric, because, as I said at the beginning, you have polar filaments. So the filaments where the motors move as a polarity. So these potentials are already inbuilt asymmetric. So they are not tracks. They are inhomogeneous tracks which have a polarity. Lecture-2 is polar.
So one way of understanding this mechanism, why it moves in that particular direction, is just imagine it's in this trap in the first. On an average, when it is on that, it is moving from left to right.
Yeah.
And then it makes a jump. then it diffuses.
Yeah.
Then when it reattaches, because of the asymmetry, it is again more likely to move to the right than to the left.
Yeah, this is what I try to explain. Exactly. So you can come down here. Okay. But the particles in average are falling here. And then when they feel the strap, maybe they don't have enough energy to jump. But they can tunnel in a way, because then they come back, but they come back, you see, through here. Right? So they have to do this type of cycles. And this is what in the end generates entropy production. You are doing cycles all the time. So you are doing a cycle like this here, come this way, come this way, come this way, come this way. So you're doing these things, okay? And this is in the end irreversibility. So this will totally relate to entropy production and irreversibility. The five. I'm doing very bad with that. You will have this motion. Okay, if you ignore fluctuations like this, okay, of course here is both, but sometimes it's like this, go down. Okay, so you have cycles and irreversibilities, and this is the key ingredients of entropy production. Will come later, is in my lecture.
So are you clearly planning to continue, or you want to break?
How are we with time?
Pretty late.
Pretty late. How much do I teach until now?
1.5 hours.
1.5 hours. Okay, I think it would be a very good moment to stop. Okay, my last lecture I promised will not come. So what I will do is I will focus on.
What did you promise for the last lecture?
That lecture was a bit more advanced from bullfrog stuff. But I think it's better I focus in motors and irreversibility.
Yes.
So the next lecture will be irreversibility with discrete information, because I will do a discrete model of this, which instead of having infinite, will have a finite number of states like this. There will be a Markov process with 6 states, and there I can explain a lot of things. This will be the next lecture, and the final lecture will be more advanced, where I can also see, okay, it's called intertransition time, so it's a more, okay, it's another analysis of irreversibility. But if I'm able to explain the simple model, ratchets, it's good. Okay, good.
Thank you. So again,